Good afternoon. In the previous meeting, we have discussed this boundary condition topic related to applicable for the electrostatics. Boundary condition means it is the condition which the field need to satisfy at the interface between this layer. Here you can see there are two layers, slab 1 and slab 2 with different mediums, medium 1 and medium 2. Medium 1 and 2 may be anything, maybe it can be dielectric combination, or it can be dielectric and free space combination, or it can be dielectric and metal it can be any combination. We have calculated the boundary conditions. Electric, dielectric, the boundary condition is the boundary condition. Tangential component should be continuous across the boundary, or there will be the tangential component will not undergo any change. Going to the normal component of electric flux, the difference between the normal component electric flux will be equal to the rho s. If you assume where rho s is a charge, surface charge exists on the boundary. If you assume it as 0, then dn1 equal to dn2. The normal component of electric flux will continue across the boundary. One more thing is law of refraction, tan theta 1 by tan theta 2 equal to epsilon r1 by epsilon r2, or the ratio of the permittivity of the medium will decide, or the permittivity of the medium will decide the refraction, angle of refraction. For metal case, the simple, whatever the boundary condition we had earlier, you need to force such condition, like if it is conductor, there will be no electric field inside the conductor, and outside the conductor, electric field should be perpendicular or normal. Only normal component of electric field will exist, but the parallel component, or the component electric field component which is parallel to the conductor, will be short circuited, or it will be 0. Now let us practice two problems to understand this idea, or how these boundary conditions are practically useful. You will get 10 mark question based on this electrostatic boundary. We will try two simple problems we will take. So let us first start with this. Take half minute to go through the given details and extract the details given. Two extensive homogeneous isotropic, these are not really required, homogeneous isotropic dielectric made on plane Z equal to 0. So plane, let us consider plane Z is 0. This is the interface or boundary. Boundary is at Z equal to 0 plane. For Z greater than 0, the medium is characterized by the relative permittivity 4, and medium 2, which is below the boundary, the permittivity is 3. Epsilon R2 is 3. So let us say this is medium 1 and this is medium 2. Then given like uniform electric field is given, E1 vector is 5AX plus 2AY into 3AZ kilovolt per meter. Such a simple problem, but every time I used to see because of a minor mistake, people used to lose mark. Almost 5 marks you may lose because of very minor mistake. So carefully please look at this. So two different mediums meeting at Z equal to 0. Above Z greater than 0, it's medium 1 with permittivity 4, and Z less than 0, it is medium with permittivity 3. Now first you need to calculate E2 vector. So one side the field is given, what is the field on the other side, right? So one side is given, what is the field on the other side? So first step is you recall the boundary condition. The boundary condition for the boundary, right? The boundary condition for dielectric boundary. What are the boundary conditions? ET1 equal to ET2. Tangential component will not undergo any change, but the normal component of electric flux also will not undergo any change, provided that there is no charge, surface charge on the surface. So here between the in the boundary there is no charge exists. Such details were not given, so you can assume and you can use this formula. So these two formulas are more than sufficient. Now let us calculate electric field at medium 2 from the electric field at medium 1. So to calculate that, you need to clearly identify the tangential and normal component. If you calculate that, then problem is solved. You need to clearly identify which are the field components parallel to the boundary, which are the field components perpendicular to the boundary or normal to the boundary. Now let me write this equation. E1 vector is there was some issue, technical issue. I hope I'm audible. Please confirm.
Yes, sir.
Okay, thank you. Now we need to identify the tangential component of E1 and a normal component of E1. Right. So now let us write the general equation E1. Okay. So which is the component tangential to the boundary? See, E1 vector is given. E1 vector is 5ax minus 2ay plus 3az. Right. So which is on this, which are the components parallel to the boundary? It is like x, y, z, right? So boundary is somewhere here. See, this is the boundary, right? Now, which fields are parallel to the boundary? I want to hear from you. Which are the components parallel to the boundary? The idea is very simple. This plane can be called as z equal to 0 plane, or you can say it as xy plane. Okay, this clue is more than sufficient, or this is more than sufficient to answer this question. Now tell me, out of these three components, x, y, z components, which are parallel to the boundary? X and y.
X and Y component.
Good. X and Y. See, this not one time, every time I can see like almost 30-40% of students used to do mistake with this and identifying this. It's a 10 mark question where you can easily score. It is not quite difficult compared to the other topics, vector topics. You can easily score, but just because of it's not properly identifying this tangential and normal component, people used to lose the mark. You guys understand? Like x and y, which is parallel to the boundary, or you can say x component and y component are the components tangential to the boundary. And which component is normal to the boundary? 3az, right? Okay, so 3az is perpendicular to the boundary. So you can say this is parallel to the boundary, this component is normal to the boundary. Now let us apply this rule or apply this boundary condition. This is the case for the medium 1, and for medium 2, E2t equal to E1t, right? So which is equal to 5ax minus 2ay. Then one part of the problem is solved. So in the medium 2, that is in this medium 2 or in the bottom, like in this medium 2, electric field tangential to the boundary will be 5x minus 2ay, the same value. Okay, same value. What about the normal component? To calculate the normal component, you have to apply this, right? You have to apply this equation, apply this boundary condition. So to apply the boundary condition, you please rewrite this. E1n equal to 3az. D equal to epsilon E, right? So E equal to D over epsilon. So D1n over epsilon 1 equal to 3az. Right? So you can say D1n vector is epsilon 1 into 3az. Therefore, what is the value of epsilon? Oh, sorry.
4, sir.
Wait. D equal to epsilon E, right? So you need to write in terms of D. So just a minute. Sorry, I lost the track. So E1n is, see, this is the normal component, right? So if you write D equal to epsilon E, so D is this much. Okay, so epsilon R1 is how much? Epsilon R1, that is medium 1, it is 4. So 4 into AZ. Right? Is this clear? So
Yes, sir.
D1n is 4. So what is D2n? So D2n equal to D1n. Right? Which will be equal to 4 times AZ. Sorry guys, it's not 4. 4 it's 4 into 3, right? 3 I forgot. So it will be 12. 12 into AZ. Okay, so what do you want? You want E normal component, right? So uh, D equal to epsilon. See, I think the space shortage is there. I will write it again. See, I'm talking about the normal component. The boundary condition is due to n equal to D1n, right? So first let us calculate what is D1n. Already we know that E1n equal to 3 AZ. Okay, so from that you can write value of D. So D equal to epsilon E. So epsilon R1 into E1n, which is 4 into 3 into AZ. Okay, so D2n will be equal to D1n. So that should be equal to 12 along Z direction. Now you want E2n, right? You don't want electric flux, you want in terms of electric field intensity. Okay, so using this relationship, E equal to D over epsilon, right? So E2n equal to D2n over epsilon R2, epsilon R2, right? So what is D2n? It is 12 into AZ over what is the permittivity of medium 2? Permittivity of medium 2 is 3, right? 3. So the answer is 4 times of AZ. So this will be the electric field in the medium 2, which is normal to the boundary. Okay, this is such a simple thing, but I think previous page there was a little confusion. Hope this is clear. This is clear. So in the
Yes.
medium 2, electric field is the normal tangential component plus normal component. So tangential component is 5ax minus 2ay, and the normal component is 4az. That's all. Okay. I take off a minute. If any doubt, you may ask. It's just very simple form of question. We just multiplication and division is sufficient, and that too in the scalar level. Okay, mathematics only required. So now first part of problem is solved. Now let us try the second part. So from the electric field in the medium 1, we have calculated the electric field in the medium 2 using the boundary condition. This is what the practical application of the boundary condition. Now second topic or second question. Angle of electric field 1 and electric field 2 which make with the interface. Without the picture it is very difficult. Please draw the boundary. This z equal to 0 is the boundary, and let us draw the normal to the boundary. So this will be the z axis, right? This is the z axis, right? What is E1 and E2? Let's not bother about E1 and E2, whether it's oriented along Z or let us not bother about. What is the definition for this? Angle, electric field making with interface. Right? Now let us say this is E1 vector. Let us say this is E2 vector. Let us draw a general picture. Okay. So this is what the angle they are asking. Okay. Angle between the boundary and the electric field. They are not asking you to calculate this angle. This is actually theta 1, the refraction angle theta 1, and this is theta 2. They are not asking you to calculate theta 1 and theta 2. They are asking you to calculate the angle electric field is making with boundary. Okay, so let us mark it as alpha 1 and this as alpha 2. So now we need to calculate alpha 1 and alpha 2. Okay, now let us calculate the angle. Now let me write the E1 vector equation here. E1 vector is 5ax minus 2ay, sorry, 2ay plus 3az kilovolt per meter, and this is the tangential component, this is the normal component, right? En, this is Et, right? So now you can decompose this into two components, tangential component and normal component. What is normal component? 3az is the normal component, and tangential component is 5az minus 2ay. That's all. Now you need to find the angle. Can you please tell the angle of alpha 1? This alpha 1 you need to calculate. What is this length? What is the length of this vector? Square root of 5 square plus
Root 29.
2. Thank you. That is root. Correct. Root 29, right? And then this length is square root of 3 square, which is 3, right? So alpha 1 equal to tan inverse of 3 over square root of 29. That's all. Give me the value in degrees. What's the angle? Give me the value. Alpha 1. My calculator is showing 29.1. See, I want to complete by 12:30 today. If you are not sharing the answer, if you are not involved, it will go up to 12:50, 12:55. No issue for me. So second part of the question, this question is angle E2, which is making with the boundary. This alpha 2 we need to calculate. Now let us write the E2 vector equation. What is E2 vector? No other way. You need to give me. You need to tell me the answer. I don't remember. What is E2 vector? I think 5ax.
Sir, 5x minus 2ay plus 4az.
Thank you. Plus 4az. Right. So this is the tangential component, and this is the normal component. Right. Now if you plot, this is the tangential component. Tangential component means 5ax minus 2ay, and this is the normal component. This is 4az. Right. So if you highlight that triangle, angle alpha 2 you have to calculate. So right angle, and this length is square root of 29, square root of 5 square plus 2 square, and this length is 4, right? So alpha 2 is tan inverse of 4 over square root of 29.
$36.6.
Thank you. 36.6. Now, see, alpha 1 and alpha 2 are the angle the fields making with the boundary. Suppose if I ask you to calculate theta 1 and theta 2, the angle of refraction, theta 1 and theta 2, what will you do? Anyhow, the same procedure only, right? You need to calculate this. That sine cos will change only. Okay, that's the difference. If you calculate, anyhow, theta 1 is 90 minus of alpha 1 and theta 2 is 90 minus alpha 2. Now I need to delete, or I can explain with this page. So what is theta 1? So theta 1 is, what is theta 1? Alpha 1 you have calculated. Same way, if you calculate theta 1, how much you will get? It will be 90 minus alpha 1, right? It will be 90 minus alpha 2. I think 90 minus some 29 degrees something, right? I don't remember the value. Yeah, 29.1 degree. And alpha 2 is 36.6 degree. So you will get, see, you can directly calculate from here. Theta 1, if you have to calculate theta 1 alone, then you can calculate like this. This will be the tangential component, this will be the normal component, and you can calculate this angle theta. But anyhow, here you need to calculate the angle between the boundary and the electric field. That's why we are considering this angle. Otherwise, we can calculate this. Okay. So this 90 minus 29.1 is 60.9 degree. And there is a reason for why I'm calculating theta 1 and theta 2 now. There is some reason. You can check the answer because it's going to be a 10-mark question. You can ensure, because in the exam, first our target is to get pass mark, right? If you get 10 out of 10 out of these 10 questions, you are almost closer to the, like, you have taken a very big step, right? So this problem, you can really verify your answer. That's possible here. How it's possible to verify the answer? Your entire answer you can verify with single this theta 1 and theta 2. Even your previous step, whether it's correct or wrong, even this alpha 1 and alpha 2 and theta 1, theta 2 calculation, also you can verify. All you can verify with this angle of refraction formula. Theta 1 over tan theta 2 equal to epsilon r1 over epsilon r2. Right? So tan theta 1, tan 60.9 degree over tan 53.4 degree is it to be equal to permittivity of medium 1 over permittivity of medium 2, that is 4. Relative permittivity of medium 2 is 3. You should you can check. Is that correct? The ratio is correct. So this is equal to 1.33. This ratio is equal to 1.33. Yeah, 4 by 3 is 1.33, right? So this is verified. So the angle theta 1 and theta 2. Now by doing this, you can verify, confirm alpha 1 and alpha 2 calculations are correct. Also this E1 and E2, whatever you have, E2 which you have calculated from E1 is also correct. So 10 mark is assured. So I suggest you to verify your answer using this relationship, refraction angle relationship. Is it clear?
Yes, sir.
Now, third part of the question, find the energy density in both dielectrics. Energy density in dielectric. The energy density formula, what is the formula? You don't need to refer anything, you can directly give the answer, energy density. Energy density in capacitor, the same formula of CV square, right? In the same way you can write of epsilon E square. So you can consider the analogy of CV square. So of epsilon square. Now in medium 1, electric field equation, see some of you give the electric field equation at medium 1 and medium 2. Medium 2 I can write. What is medium 1 electric field equation? See, we are exaggerating the problem. We need to give 10 mark, right? Just for this steps we can get 10 mark. So give me the equation, E2V1 vector equation.
So for medium 1, it is 5ax minus 2ay plus 3az.
Thank you. Right? So epsilon R1 for energy density, let us use W. Density equal to of epsilon R1 into E square. This 3, right? Epsilon R1 equal to 3, right? 3 square root of 5 square plus 2 square plus 3 square whole square. See, the square sometimes you may forget to put, so the E square is there, right? So magnitude of E square. So give me the value. Same way you need to calculate for the medium 2. E2 vector is 5ax minus 2ay plus 4az. So energy density W, the energy density is equal to half epsilon R2 into E2 square. So for medium 2, the permittivity is, relative permittivity was 4, I guess 4, and magnitude of the value, this E vector is 5 square plus 2 square plus 4 square whole square. Guys, there is yeah, I think I have deleted, there is a mistake. See, I write like of, please listen to this, energy density, the formula which I wrote like of epsilon E square, right? That's correct. It is epsilon. It is not epsilon r. In the previous slide, I consider epsilon as epsilon r. That's not correct. Epsilon equal to epsilon naught into epsilon r. Okay. If you consider for medium 1, epsilon 1 equal to epsilon naught into epsilon r1, where epsilon naught equal to 8.854 into 10 power minus 12 multiplied with epsilon r1. Medium 1 relative permittivity is 3. Okay, so that you need to plug. Okay, so energy density in medium 1 is equal to of epsilon 1 into E1 square. So there is a mistake, please update this. So don't ignore this. So here it is epsilon, it's not epsilon r. So energy density in medium 1 and 2 is this quantity, joule per volume. So up to this it's clear. Now final part of the question. Energy within a cube of side 2 meter centered at 345. How will you calculate this? I'll give 1 minute time, think. What is this? Energy density within a cube of, sorry, energy, it's not energy density. So the energy density is given, you need to calculate the total energy. Energy, let us take total energy equal to, if you integrate the energy density over the volume, then you will get the total energy. Is it clear? Now, what is the volume? Or you need to integrate over the cube of side 2 meters centered at 3, 4, minus 5. Then what should be the x limit and y limit and z limit? Please try. See, centered at 3, 4, minus 5. If side is 2 meter, all sides, then what should be the limit of integration? So it should be from 2 to 4. So it's like plus minus 1 you have to do, right? So it should be from 3 to 5, and that should be from minus lower limit to upper limit, right? So it should be minus 6 to minus 4. Minus 6 to minus 4. Now at least you answer this. What should be the, okay, here it will be dx, dy, dz. Now what about this value, energy density? Which value you will use? In the previous slide we have calculated energy density for medium 1, for medium 2. So above boundary it's medium 1, below boundary it is medium 2. You have calculated energy density at medium 1 and energy density at medium 2. Both answers available. Now which density you will consider? Will you consider both, or you will consider medium 1, or you will consider medium 2?
Medium 2, sir.
Why?
So because Z is less than 0.
Yeah, correct.
Minus.
Thank you. Exactly correct. So Z greater than 0 is medium 1 and medium 2 is Z less than 0. See this point where this cube, if you consider this cuboid, where this cube lies, it's from 2 to 3. Don't bother about this x, y, but where is Z? Z is from minus 4 to minus 6. Okay, Z extend from minus 4 to minus 6. So that should be in the bottom, or that should be in the medium 2. Okay, so this value should be energy density which you have calculated for medium 2, that is 597. So you need to put 597 microjoules per meter cube. Not only here, whenever you have some plane means it's infinite. Whenever you have plane, you look at only the uh, um, like if in this case is that you need to look at only this value. You don't bother about x and y. It can be anything, but this z value decides whether you are in medium 1 or 2. So it's really, you need to least bother about this, but you need to careful about this z, because anyhow this x and y is going to be parallel to the boundary, right? So this z value will decide whether you are in the one side of the boundary or other side of the boundary. Any questions?
So can you explain how you have taken the limits?
Yeah, sure. See, it's like z. So there is a cube. The center is 3, 4 minus 5, and the side of the cube is 2 meters. So length, width, height, everything is 2. Right? If the center is 3, 4, 5, what about the height? See, x, this is x, right? Like this is x, y, z. So x is 3. Then if the length is 2, the center is somewhere laying here, right? So it is 3. So 3 minus 1 is 2, and 3 plus 1 is 4. Okay, so that should be from 2 to 4. Right? Same way for
Oh,
y.
okay, sir. Okay.
Okay, same way for y and z you need to do. Okay, plus minus 1. Because it is centered, the center is given, that's why. The center is given.
Okay, sir. Got it.
So if you put the values, then you will get even see this integral dz, really that not matters, right? In this case, sorry, once you plug only, you will understand the importance. You don't need to even do that, like do the integration, because you know the side length is 2 meter, all the sides, right? So integral of this will give you 2. So even you don't need to take that much pain, but still you need to identify which medium we are doing the calculation. See, I'm repeating, in this integration, really we are not going, you no need to do the integration, because already you know integral of dx equal to 2, integral dy equal to 2, integral dz equal to 2, right? Because it's cube of 2 meter length on all sides. That's all. So I hope you understand this. So you need to understand which is in the given field, which is parallel to the boundary and which is normal to the boundary. That's all. Now another example. Please try. Even without touching pen and using pen and paper, you can give the answer. It's a 5-mark question. Without using pen and paper, you can give the answer. I'll give 1 minute time to think. You no need to align with this x, y, z. For your okay, maybe you can align with this, no issues. Now let us take this coordinate system. Region y less than or equal to 0 consists of perfect conductor. Right? Y less. Let me take this. Y less than equal to 0 is a P is perfect conductor. So this is a conductor. And while the region y greater than 0, that is this side, is a dielectric medium with a relative permittivity of 5. So this is dielectric, right? So this is the boundary. And surface charges is given. This is the conductor. So the surface charges is given. So surface charges here is 2 nano coulomb per square meter. First, we need to calculate D and E at a point A, at this point A, 3 comma minus 2 comma 2. I told this picture is sufficient. Without using pen and paper, you tell me the answer. What will be the electric field at 3 comma minus 2 comma 2?
It will be 0, sir.
Exactly correct. How?
Sir, because it's in conductor, sir.
Exactly.
And
So
it lies.
exactly, it's lies inside this point 3 minus 2 2. So this is what you need to look at. Don't bother about the x and y, so x and z. You need to only look at this minus 2. So it's lying on the conductor. Inside the conductor, electric field is 0. Okay, so at electric field at 3 comma minus 2 comma 2 will be 0. If E is 0, then D also 0. Done. One part of the problem is done. Now second part of the problem. At this location minus 4 comma 1 comma 5. So minus 4 comma 1 comma 5, let us say this point A will be here, the point B will be somewhere here, right? That will be in the medium 2. That will be exist in the dielectric. Okay. Now what is the D and E? At point B, which is lying in the right side of this picture, like right side or in the dielectric. This point is lying in the dielectric, point B. What is D? So D and
Sir, D,
this is like, let us
D
say
will be
this
sir 2 nano coulomb.
rho
2
S,
nano.
right? Pardon?
Yes, sir. Yes,
Rho
sir.
S.
Rho
Good,
S.
good. Yeah, exactly. Rho S. Okay. For the dielectric and conductor boundary, this is the formula. Electric flux normal to the boundary is equal to the surface charge density. Surface charge density in this case is 2 nano coulomb per square meter. One part of the problem is done. What is the other question? Electric field you need to calculate, right? So D equal to epsilon E. So epsilon, that is epsilon naught into epsilon R into E and 2 equal to, sorry, this is what, sorry guys. D equal to epsilon E. So you want E, so E equal to D over epsilon. Okay. I'll continue here. What is D? So we are calculating the normal component, right? Normal component on the medium, let us say B. This is medium B, right? Medium B. So it is 2 nano coulomb per square meter over uh, electric field, epsilon, that is permittivity on medium B. So epsilon equal to epsilon naught into epsilon R, which is equal to 8.854 10 power minus 12 multiplied with this value, epsilon R. That is, what is the value? 2. So you need to be careful about this epsilon. Hope this problem is, we are clear with this. Take half minute. If any questions you can ask. Now into the last slide. Please give the answer for this question. Read the statement. Some 6 pictures available, where it is like medium 1 and 2. Shaded grade region is medium 1 and light region is medium 2. Uniform fields. Now read the statement. The uniform fields shown in figure are near a dielectric boundary. So in all 6 pictures, it is dielectric boundary. Let us say epsilon R1, this is epsilon R2. In all pictures, upper medium is epsilon R1 and lower medium is epsilon R2. Which configurations are correct? The condition what given is, further detail what given is, assume that the boundary is charge free, there is no charges on the boundary, and epsilon 2 is greater than epsilon 1. Right? So epsilon R2 will be greater than epsilon R1. I'm highlighting again, epsilon 2 is greater than epsilon 1. So this will be epsilon 1 and this will be epsilon 2. Then which picture is not correct? See here electric field, as you can see D is given. In the first three pictures D is given and remaining three pictures E is given. Which picture is not correct? What do you understand from this picture? I will give the clue. You can see in this picture electric flux is in this direction, then in the medium one it is bent, right? In the second picture electric flux is in this direction and medium 2 is also in the same direction, it is continuing in the medium 2. Picture 3 it's bent, picture 4 it is bent, it may be bent toward y or z. Okay, so anyhow it is bending, electric field is bending. Now here electric field is bending toward this direction, again electric field is bending some angle toward this direction. Okay, here electric flux is bending, here electric flux is bending, but here electric flux is not bending. Okay, so which case is wrong for this condition? Epsilon 2 greater than epsilon 1. Which picture is wrong?
Sir, B and E.
Exactly.
B and
Why? B and
E.
E. Now, can you say
Yes.
why E is not correct? First B. Let's start with B. B. Why is not B is correct?
Sir, because there is no bending.
Exactly. So, from which formula you can answer this, or which formula will just give justification for your answer? There is a simple formula available with us, right? Tan theta 1 over tan theta 2 equal to epsilon or epsilon 2 or epsilon 1 by epsilon 2, right? See, this ratio epsilon 1 and epsilon 2 are different numbers. If they are different numbers, then theta 1 and theta 2 should be different, right? See, this ratio, numerator and denominator
Yes.
is different. Then here also the numerator and denominator should be different. Then what should happen? Theta 1 and theta should not same. Or we can say this is theta 2, this is theta 1. Theta 1 and theta 2 should not be same. Then this picture is not correct. Okay, now why you have suggested this picture?
Sir, actually I took the example of light, sir, when it moves from denser to rarer medium.
Oh,
So
good. So epsilon 2, epsilon 1, so it is denser medium, right? This way you used to say. Denser to lighter medium, so light will bend toward which direction?
away from normal, sir.
Away from the normal.
Yes, sir.
Correct. Or you can check mathematically here, right? If you check mathematically, denominator is, in this case, this is theta 1, but theta 2 is less, correct? Which is greater in this picture? Theta 2 is greater. Or, sorry, it's difficult to say. Which is greater? I can't understand from this picture. Sorry, I think it's difficult to say which is theta 1 which is greater or theta 2 is greater. But anyhow, your answer is correct. Okay, or else you can check with this theta 1 over theta 2 equal to epsilon 1 by epsilon 2. So in this case, epsilon 2 is bigger, that is denominator is bigger, right? It is larger number. So in this case, theta 2, this is theta 2, this is theta 1. In this case, visually you can say theta 2 is larger, right? Theta 2 is larger. Then
Yes.
how the theta 2 is larger? Tan of uh, when the angle is increased, what will happen? The denominator will increase, right?
Yes, sir.
Yeah, the denominator will increase. So we don't know the value, so we can't conclude, right? Here also denominator is increasing, here also denominator is increasing. So we don't know whether it is going to proportionally increase or not. So without knowing the angle theta 2, we can't give the answer. But even your answer is correct. Without, like, visually your answer is correct. But if you are not sure about that, epsilon value is not given, we can say this answer is the wrong answer. Okay, remaining are correct,
Okay.
and this probably we don't know. The epsilon 2 is not available, but you are correct. It should be bent toward the denser medium, right? It should be bent toward the denser medium. Okay, that's all. So you will get one 10-mark question based on this. So be ready with this. You can practice these problems, or even some practice problems are available in the textbooks. You can try. So with this chapter, with this topic, we are concluding the electric field and medium. or electric field in non-free space or non-vacuum medium we have discussed. So next we will migrate to a topic called boundary problem, where we will calculate the capacitance using some condition that we will discuss in the next class.
Okay,
Any
sir.
questions? Okay, thank you. If any questions you may ask, or I can leave now.